Let's get started with some examples using Octo Python, which is our lightweight MapReduce implementation that we shall be using for our programming assignments later this week. Let's take a look at how the word count problem can be expressed in Octo Python. This is a slight modification of the file which you'll find on the site as a demo example. The directory Gutenberg small contains a bunch of small text files, much smaller than the ones which are available on the site, so that we can actually execute this program in a few seconds rather than a few hours. Notice that we have defined two functions, a map and a reduce. The map function takes a key value pair and emits other key value pairs, and so does the reduce. Let's see what the map function is doing. The key in this case is the document ID, or the document name, the file name here, and the value is the contents of that file. For every line in that file and for every word in that line, the map function emits a pair, which is the word itself in lowercase and the count of 1. The reduce function gets a bunch of key value pairs as well. In this case, the keys are the words and the values are lists of counts that it's getting from many different mappers. The reduce function also gets a bunch of key value pairs from all the mappers. In this case, the keys are words and the values are the counts, which are just the ones emitted by the mappers. And so for every word, all the reduce function needs to do is figure out how many mappers found that word, how many times, and all it needs to do is figure out the length of the list of values it gets from all the mappers for a particular word. Notice that the map functions are emitting counts of 1, so it's okay for the reducer to merely sum up the lists of values that it gets from all the mappers. We'll now run this MapReduce program using Octo. This terminal is the server, so when we start it by simply calling the Octo code with the keyword server and the program that implements the map and reduce functions, which is our program here, a server gets started waiting for clients to join. We have two more shells where we will start clients by merely calling Octo with the client keyword and telling it which server to connect to, that is, which machine the server is running on. The server in our case is running on this very machine itself, so we use localhost as the address for the server. Let's start each of the clients, and as you can see, they are performing different map tasks on different files, and then finally they cooperate to perform all the reduce tasks, in the end writing the totals to a file as well as to the screen. So, for example, they have computed that across all these files there are 4 occurrences of you, 2 occurrences of yet, and many others which have scrolled up beyond our view. The rest of this code is merely used by the server to set things up. In particular, a source dictionary needs to get created where the key value pairs that each mapper needs to get are kept in a dictionary. So here we have the file name as the key and the file contents as the value for all the files in the directory Gutenberg small. Notice also that both clients and servers get the same program. It's just that the clients implement the map and reduce operations, and the server merely gets data from where it needs to find it and sends it out to the mappers, and finally accumulates the data from the reducers and prints out the results. When you run this code for yourselves, Some of you will notice that the mappers, or rather the processors in the map phase, are only implementing mapper operations and emitting counts of 1, rather than, as we have described earlier, performing partial reduce operations on whatever documents that they manage to get data for. Let's see how much data is actually produced by the map phase because of this behavior. Each word is emitted by a mapper multiple times. In fact, if the size of the initial set of documents is D, including every occurrence of every word, after processing by mappers, again, exactly that much data is produced because each word is emitted every time it is seen. On the other hand, in our earlier implementation or description of the word counting problem, this was not the case, since the counts within each map process were actually summed up before moving on to the reduce phase. This process of reduce operations being performed partially within each mapper is called a combine phase. In other words, when you sum up the word counts for every mapper before emitting, you're implementing the reduce function as a combine function before the data gets sorted by the MapReduce system. The result of this is a reduction in the amount of intermediate data which is produced, which will lead to better parallel efficiency of the MapReduce process, as we'll see shortly. Let's see if we can modify our Octo program to implement a combine phase where partial reduce operations are performed before passing the data on to the actual reduce phase. Unfortunately, Octo doesn't allow for a separate combine operation like the map and reduce functions. However, we can simulate the combine process by ensuring that each time a map function is called, it keeps track of its results in a local variable w. The reason this is possible is because of a peculiar feature in Python called the iterator, where a function that instead of returning a value yields a value stays in memory, and all its variables defined remain available next time the function is called with exactly the same set of inputs. And the function begins implementing exactly where it left off the last time. So let's see how this works. Every time the map function is called for a particular document, it adds up the word counts for all the words that it sees in that document and stores them in this dictionary W. And then it goes through all the words that it's found in this dictionary with counts and yields them as key value pairs. When the yield operation is called, the function actually returns this value to the caller, which is the Octo program. The next time the Octo program asks for a value, it yields the next count, and so on and so forth. In a sense, this is implementing the combiner within the map function. A little bit of cheating, because in real MapReduce implementations, we actually have a separate combine function in addition to the map and the reduce functions. Let's now run our modified combiner enabled MapReduce task. We start the server, and then we start each client in turn. As you can see, they are performing the map and then the reduce phase, and now we're done. You might not have noticed earlier, but the server is actually printing out the time the combined MapReduce task actually took. In this case, it was 12 seconds. The actual Octo program available from the site doesn't have this timing, so I would encourage you to try to look through that code and insert the timing so that you can reproduce such results. Further, do look back and figure out how much time the word count program without the combiner actually took, and you'll see that the combiner phase actually added a lot of efficiency. Last but not the least, it's very important to realize that the combine function can work only if the reduce function is a commutative and associative one, because we don't know which order these reduce functions are being performed in on what data. So any reduce function which relies on the fact that the function is applied in a particular order on all the values for a particular key will not be able to be split up into a combined phase for efficiency purposes.